My name is Anderson. Today I'm going to talk about this paper. So what is the Capped Simplex? This is the definition. This is be denoted by delta K, where K is the parameter. We use the standard notation, so 0 and 1 just represent the vector of 0 and 1. Inequality is taken elementarized, and etc. Geometrically, Capped Simplex is just a cube with a corner being chopped off. So for example, for the leftmost figure, if K is too small, that means the half space and the cube did not intersect. In this case, delta K will be empty set. And for the rightmost figure, when K is large enough, then delta K will be just the cube. For the middle figure, for some suitable K, then delta K is representing a hypercube with a corner being chopped off. We also denote that if we replace the half space by the hyperplane constraint, then this delta K with an equal sign means it is the intersection of the cube and the half space and the hyperplane. So for example, in three-dimensional case, the intersection will be this triangle. So the goal of this paper is basically try to study how to project onto this delta K very fast. And this problem may look easy and simple at first glance, but actually this problem is not trivial because the delta K is a combinatorial in nature, and therefore projection onto some similar type of polytope such as the unit errand ball and also the simplex. Usually the traditional approach will use some sorting-based method which have higher cost, and in this work we don't use sorting. Instead, we use some numerical method. And then we also find that by applying this kind of proposed fast projection method into some sparse regression, actually the resulting method for solving some bioinformatics problem has very good results. So we now talk about the mathematical idea. So one is the problem, projecting onto the Capped Simplex. By definition, delta K has two constraints, the green one and the red one. The green one is easy, so we keep the green one as in the constraint. But for the red one, it is the one that making the projection difficult. So we use Lagrangian multiplier and add it into the problem. So we form the partial Lagrangian problem as 2. Problem 2 has two variables, x and gamma. So there are two subproblems, one on x and one on gamma. For the subproblem on x, actually we can solve it exactly with closed form solution. So this is the expression of the closed form expression. And then that means what? That means this is actually the relationship between x and omega. And if we put this x and omega relationship back to the problem 2, actually we will reduce and eliminate the variable x. And therefore, now problem 2, after we plug in this new x star relationship, then we have problem 5. Problem 5 is just the Lagrangian with the x being removed. As a summary, that means what? That means we have problem 1, and after all the manipulation we introduced before, we now have problem 5. Problem 5 is just a problem on the omega gamma. Omega is a function of Lagrangian. The Lagrangian function we see before, but just with the x being eliminated. So this is totally a function on gamma alone, and gamma is just a scalar variable, and therefore we change the vector problem into a scalar problem. And the traditional approach on solving a similar type of projection, for example, some paper on solving projection onto unit simplex or unit errand ball, will stop at here, and they will continue on solving the problem by solving omega prime equal to 0. That is, they will solve the omega prime, that means the gradient of omega with respect to gamma equal to 0 by some sorting, because omega function will be a piecewise linear function. But in this work, we do not use sorting to solve this problem. We will instead solve problem 5 directly using numerical method. So that's the contribution. Mathematically, we will derive the derivative of this omega function, which is not trivial. And we found that actually the Lipschitz constant of this omega prime, that means the gradient, is the Lipschitz constant of this gradient grows in linearly as On. And then algorithmically, we solve this problem 5 by Newton's method. As we said before, traditional approach on solving the projection problem will try to solve the omega prime equal to 0 by sorting, which has very high cost. But if we solve it by Newton's method, the per iteration cost is just On, and assuming there are t number of iterations, then the whole cost will be just TON. And we found that empirically, if n is very big, the proposed method is very fast. And because the method is very fast, that's why it finds application in sparse regression such as bioinformatics. For example, we found that empirically, if we use the proposed projection method to solve some bioinformatics problem on gene identification, then we can reduce the runtime from half hour to just 3 minutes. We will talk about this in the following. So first, we'll talk about the main theorem. So this is the main theorem, which is related to the gradient and Hessian of this omega function. So this is the expression. And for details, please refer to the paper. And then here is the algorithm. If you look closely, it is basically just the very simple Newton's method. So first, we define gamma 0 by some initialization, and then in line 3, we define an intermediate vector v, which relate the input vector y and also the gamma. Then in step 4, we perform the Newton's update by computing the gradient and also the Hessian. So the whole algorithm, the main cost is just line 4, and with the per iteration cost of On, linear cost. And assuming it takes t iteration to converge, then the whole algorithm will take t times On number of costs. Theoretically speaking, t can be as large as infinity, but practically speaking, we observe that t is very small in all the experiments we conduct. So that means low per iteration cost with a small t means fast. In comparison, existing method on solving this kind of problem use some sorting method which cost can go up to On squared. That means very slow, especially for the case when n is a very big number. And lastly, this algorithm is for the case projecting onto delta k equal. If you want to project it onto delta k without an equal sign, that means the k capped simplex, then you just need to replace in line 4 the gamma with the gamma plus. That means you take it with max with 0. So now we will talk about some details. So you may wonder why we use Newton's method but not just gradient descent. It's because by the theorem 1, we found that the gradient has a Lipschitz n, Lipschitz constant n. So that means what? That means for the step size, that guarantee convergence will scale as 1 over n. So if n is very big, for example, in big data, n is very big, so 1 over n will be a very, very small number. And in that case, we observe that very slow convergence in gradient method in many experiments, and that's why this inspired us to switch to Newton's method. And then there are also other details. For example, the feasibility of the problem, the feasible range of gamma, how do we initialize the gamma 0, blah, blah, blah. Please refer to the papers for the details. And then lastly, in the remaining time, I will talk about the empirical result and the application in bioinformatics. So first, we will talk about the proposed method is much faster than other projection algorithm. Faster in what sense? Faster in the sense of solving this problem 1. So this table shows the runtime in seconds of different methods on various size of vector over 100 random trials of experiment. So we have 4 methods, the quad-pro, that means the quadratic programming, a general purpose solver in MATLAB, C++, which is a paper that previously studied the projection onto the Capped Simplex, and they wrote their code in C++, Ruby, a commercial software, and the proposed method. You can see from this table, basically the proposed method beats all the other methods in terms of runtime. Here, you can see that the proposed method has not just one order or maybe few order of magnitude different compared to, let's say, quad-pro and C++, and also one order of magnitude faster than Ruby. And you can see for those big size problems, for example, in the second row, the other methods are so slow that we don't even try to compute it because it's too long of time. But for the proposed method, it's still very, very fast. And for the experimental setup, please refer to the paper for the details. And this table shows the proposed method only takes a few iterations to solve the projection. For example, for the right columns, here the setting is that we have a vector y with 10 to the power 6 number of entries. And then we fix this n and varying the k in the Capped Simplex parameter. So we varying all the k, and you can see that it takes less than 1 second to solve the problem to some numerical precision. And also, if you look at the number of iterations, you can see all of them is less than 12 iterations, meaning that the proposed approach only takes a few iterations to solve the problem. Again, for the experimental setup, please refer to the paper for details. And then the following is the time plot on showing the performance in terms of runtime. And you can see that in the blue curve are the GWAS method and the red curve are the proposed method. You can see that the proposed method run much faster than the blue one in different kind of setting. For the setting in this experiment, again, please refer to the paper. This graph is basically just to show that the proposed method runs very fast regardless of the experimental setting. And lastly, we'll talk about the application in sparse regression. In bioinformatics, there's a problem called P star here. That is the first equation in the slide. And this is called a cardinality constrained L2 square regularized regression, which finds some application in bioinformatics, especially in, say, gene identification. So basically, it's a sparse regression problem. And then recently, there's a paper suggests that we can relax this P star to the following PBR problem. So notice that in the PBR that require you have to be inside the Capped Simplex. So this is exactly the problem that the proposed projection finds application onto. And actually, in fact, this is exactly the motivation behind the study of the fast projection. So here, this figure is showing that on solving the PBR, that is the problem listed here, with different projection, that is the GWAS projection in blue and the proposed projection, we solve the problem using Projected Quasi-Newton's method using the two different projections. You can see that the runtime, the blue one is always much faster than the blue one, with an order of 1 or 2. And this shows that the proposed projection problem runs much faster than the GWAS. And then here, this figure shows the performance in terms of accuracy and relative runtime. For details, please refer to the paper. The take-home message is that the proposed method can solve our bioinformatics problem with higher accuracy and with lower runtime. And then lastly, this table shows that the performance of the proposed method to solve some simulated genetic problem using the GWAS dataset with some setting. The proposed method always has the highest number of accuracy. That is, it has the highest number of correctly identified gene. Here, the setting is that there are 25 SNPs, and then there are some gene randomly mixed together with some different level of correlation, high LD, mixed LD, and low LD. And for the free method, lasso, elasticnet, and PBR always has the highest number of correctly identified gene, which is 25, and it also has the low false positive rate. For sample size equal 1,000, that means high number of sample, PBR always has the best performance in terms of correct number of identifying the SNPs and also the lowest false positive. For low sample size with 100, PBR still has the highest correct number of identifying the genes, but it does not have the lowest false positive rate, but it's also very close to the lowest positive as in the lasso. Lasso model also have the lowest false positive, but the correct number of genes identified is very terrible. So this basically means that the proposed method has a very good performance for the biomedical information. And lastly, a summary. So the take-home message is very simple. Newton's method can solve projection onto the Capped Simplex very fast. And then we introduce this method because this method is fast due to the fact that it has low per iteration cost and empirically low iteration complexity. So that's why it's very useful. And we found that in terms of bioinformatics application, the proposed method can improve the Projected Quasi-Newton to solve the bioinformatics problem very well.